All right, everybody. Welcome back to office hours. I'm sorry we had to move it 10 minutes earlier today. I have office hours I have to get to at 12:50, so just want to make sure we have time to cover our session today. Yeah, so today's going to be very visual. So you're actually going to see me today, and we're going to demo some of these models so that you can actually like understand it instead of memorizing it. I always think that's helpful. So the first thing that we're going to do is name these two compounds. So you guys should be pretty good at naming these alkanes or cycloalkanes. They're really easy as long as you know how to do the rules. So let's just jump right into them. So the first thing that we always want to do is identify the longest carbon chain. And you know, a common trick on all of these exams, especially when it's your first time doing nomenclature, is you typically go left to right or right to left. I mean, that's how you read things. So your innate tendency might be to go 1, 2, 3, 4, 5, 6, 7. Okay, or maybe the opposite way, 1, 2, 3, 4, 5, 6, 7. And this isn't a heptane because I see a longer carbon chain and I see maybe 1, 2, 3, 4, 5, 6, 7, 8, 9. So I definitely see a nonane, in there. So now the question stems, do I start from maybe the right side or do I start from the bottom side going up? And we're definitely going to start from the right because we're going to encounter a substituent at 2 rather than 1, 2, 3, 4, okay? So we see that, I'm just gonna admit more people into the meeting, one sec. And yes, okay, so we should number it like this, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, and does somebody have a question? I think that microphone's muted. Okay, and we're gonna name this with our substituent positions in front. So we see a methyl on 2, a methyl on 6. So this should be a 2,6-dimethyl because there's 2 of those. And there's a nonane, so nonane. Okay, so this is 2,6-dimethyl nonane. Can someone mute their mic? I don't really know who it is unless you're asking a question. Okay, so then the next thing that we're going to do is we are going to look at this cycloalkane. And this is kind of, I find these easier. So we basically want to pick number 1 so that whichever way we go, clockwise or counterclockwise, we're going to give all of these substituents the lowest set of numbers. So it doesn't really make sense to start here. It doesn't really make sense to start here. It always makes sense to start at a substituent. Okay, and I know I'm probably going to start either here or here because I'm going to be able to go 1, 2 or 1, 2. Does that make sense? Clearly, when you see 2 adjacent substituents, it's a good start. It's a good idea to start there with your numbering. So now I've got to think in terms of alphabetical order. So this looks like a common group that I should know. Okay, remember isobutyl was the one that had well, I guess I'll just draw it up here. That was isobutyl. Remember that extra carbon for isopropyl. So then if I move that to a different carbon, we call that sec-butyl. Okay, so this is definitely a sec-butyl. And I'm going to underline what you alphabetized it by. That's the B. This is a methyl, so I'll put M. And this is an ethyl, E. Okay, so it definitely makes sense for me to go 1 because the butyl comes first, 2, 3, 4, 5. Okay, because then we give 1, 2, 4, our substituents. So let's alphabetize it in our name. So we would say 1 sec-butyl, okay, 4 ethyl, 2 methyl, and this is a pentane, so cycloheptane. Okay. So I hope you guys followed that. This is what we did is we wanted to give the substituents encountered the lowest overall set of numbers. And in order to do that, we had to kind of just fast forward a little bit and see what the names of each one of these substituents would be. And then that kind of gave me a little bit more insight into how I should number this. Okay. And as you can see today, we're going to deal with these models. And this is the ball and stick model for water. So funny little thing right there. Does anybody have any questions on nomenclature at this point? Great, and you only get better with practice. So there's a whole bunch of practice in the workbook. I think there's some extra practice problems, Canvas maybe, Dr. Havenick's problem set. So you definitely have a lot of practice problems there. Leah, when there is a cycloalkane, instead of naming the longest chain, we name according to the cycloalkane. Correct, yeah. So the longest carbon chain is only in linear systems. So that would be, you know, the thing that we did right here on the left. And then when you're dealing with cyclic structures, you only deal with the members of the ring in the name. So if there's a 5-membered ring, it would be a pentane. If it's a 6-membered ring like this, It'd be a cyclohexane, and this would be a cyclobutane, cyclopropane, etc. What if the substituent is longer than the ring? Doesn't matter. Caroline, does not matter. It's still always conventional based on the number of the number of carbons in the ring. Yep. All right, good questions. All right, let's jump into these models. Okay, so you guys are going to have to bear with me because I'm trying to do this through Zoom. Normally I don't do this through Zoom, but let's see. I am muted. Sorry, guys. Okay, are we good? Can you guys hear me okay? Perfect. Okay, and I got some more people coming in. All right, let me submit these people. All right, so if you have your models with you, you guys don't need them, but you guys can just follow along with me. We're gonna first take the structure of butane. Okay, so butane looks like this. Okay, so in line angle, butane looks like that. So it's just 4 carbons, 1, 2, 3, 4, okay? So what we're gonna do today is do something called conformational analysis, and this is like Newman projection stuff. So this is butane, okay? So I basically took this 4 carbon linear form and I made it into this model, okay? So let me kind of talk about this for a second. Sabrina, what can't you see? Can everybody else see me okay or no?
No, we can't see your paper.
Oh, you couldn't see the paper? Gotcha. So this is butane. So 1, 2, 3, 4 carbons. Okay, good. And I just made it this model right here. So let's kind of analyze how this is also butane. So the black balls are going to be carbons. So 1, 2, 3, 4. And the white ones are going to be, oops, hydrogens. And the white ones are going to be hydrogens. So it kind of makes sense now that at the top, you know, it's the CH3 group. At the bottom, it's a CH3 group. And then the 2 carbons in between are the CH2s. And that's exactly what we see here. Okay, so we see a CH3 at the end, another CH3 at the end, and then it's 2 CH2s in the middle. Okay, so does everybody kind of follow me on how this is butane? This is important. So 4 carbons, and all the white things are hydrogens. Everybody good on that? Can somebody put in the chat box? Yes, you guys are good? Cool. All right, so what I'm going to do now is I'm going to take a modified version. Actually, we'll start with this for now. Okay, so what we're going to do with Newman projections is we are going to look down this bond axis. Do you see this? This is 2 and 3, carbons 2 and 3. So we have 1, 2, 3, 4. So we're going to look directly down 2 and 3, and we're going to see what we observe. Okay, so I'm going to basically, this is how you guys need to do it. So you need to put your head where you guys are looking right down this bond axis. So I'm going to try and hold it like this so you guys can see. So I'm looking right down carbons 2 and 3. You guys see that from this profile. And I can rotate for you guys. So this would be what you guys should do. So here's 2 and 3, and you guys should look at it like that. Okay. So do you see that? You are going to move it so that you guys are quite literally looking down that bond axis. Okay. So to make this clearer, because there's a whole bunch going on, I have a modified one. Okay. So this is butane again. All right. And just bear with me. I know this might be a lot of visuals and stuff, but it's definitely going to help in a second. Okay, so this is also butane. And the blue, I'm just going to say, is the front carbon. The black is going to be the back carbon. The orange is the front CH3 group. And the green is the bottom CH3 group. Okay, so does that kind of make sense? So all I did is I took this bigger one and I just condensed the end CH3 groups to either an orange or a green. Okay, is everybody kind of following that? All I did was take this whole chunk and make it green, and this whole chunk and make it orange, okay? And then all I did was color code the front and the back, blue and black, okay? That's all I did. All right, so let's kind of talk about what we're doing here. So normal butane, when you look down that bond axis, you're gonna see something like this. And now you guys might see why I was trying to make it look simpler for you guys. So when you look down, it kind of looks like this 6 kind of octahedral structure, okay? So we went from butane like that, so carbon 1, 2, 3, 4, and when you look at it like this, it kind of appears like this 6 octahedral type structure. And that's what a Newman projection is, okay? So let's kind of draw that. Oh, I guess you guys can't really see that. So our dot, when you draw, and I'm gonna show my paper in a second, the dot that I'm drawing is the front carbon. So let's just say, for all intents and purposes here, it's gonna be the black carbon, okay? So what I wanna do here is say, I drew this little eye, and I'm looking down 1 and 2, okay? So my front carbon is this black carbon that I'm gonna say is number 1, okay? So if I'm looking down here, this is the dot, what do I see going directly down? Okay, I see that green CH3 group. Okay, so on my little drawing, this is the first step I'm gonna do. A line down, a CH3, okay? And then, when I'm still looking at this, I see that I have a hydrogen going up to my left and a hydrogen going up to my right. Okay, so that would make sense for me to do this. Okay, so does everybody see how this, which let me get in the right thing in front of the camera, how this translates to that front carbon? The green is the CH3 down, and then the 2 white, I guess, spheres are going to be hydrogens, okay? So that's how I got the first kind of depiction. I'm only looking at the black carbon right now. So that would be the 2 hydrogens going left and right, upwards, and then the green CH3 going down. Is everybody good on that so far? Good. Okay, so then the back carbon is going to be the blue one, okay? And on paper, we denote that with a sphere, okay? So this is like the back carbon. And if you wonder where that comes from, it's like, imagine a eclipse. So I don't know what I have over here. Sure, let me do like, okay, moon, sun is farther away. So what happens is like, I guess I need something bigger than that. Here, let me use this here. Sun, this is my beads case, oh no. And this is the moon. So as the moon comes in front of the sun, like during an eclipse, notice the back carbon, since it's bigger, we're gonna denote by a bigger sphere. Does that kind of make sense? So the front carbon, which would be like the moon, is the dot, and then the back carbon, which is larger like the sun, is a sphere, okay? So that's where this sphere comes from, okay? So let's look back at that model now. So we were here, okay? And now we're looking at the back carbon, so this blue one. So I'm kind of like lowering it a little bit so you can see. So you see on this back carbon, it looks like that orange CH3 is coming directly up. And then now these hydrogens are going down to the left and down to the right, okay? So that's important. So on our paper, it would translate to that. So notice how the front carbon, it kind of intersects at the center. That's the hydrogen, the CH3 going down. And then on the back carbon, we had that CH3 going up and that hydrogen also going down. So let me just show you this model one more time to prove that to you. So we are here, all right? So I hope you guys can kind of see this. So the front carbon is that black carbon where it's that dot in the center, 2 hydrogens up and the green methyl going down. And then on the back carbon, which is the sphere, it's the blue one, there's 2 hydrogens going down to the left and to the right, which we see right here where my middle finger is at. And then also on the back carbon, that blue ball, we see we have that orange ball going directly up. Okay, so that's that. So that's pretty much how we're gonna do these Newman projections. It's very visual, but you're gonna get a lot better and you don't really need these models to get these right. It's just I'm proving things to you right now, okay? So I'm gonna switch back to the document camera and then we will come back and we'll do more visual stuff in a sec. Okay, so give me a sec. All right, and so I think I got a question here. Are we allowed these on the exam? And no, you are not allowed these on the exam. They're just good to kind of understand the theory right now. Is this, yeah. It's just good to understand the theory right now, but not necessarily good for your test because you won't have them. Okay, so again, this was butane, that's what we were doing, okay? And let's number these 1, 2, 3, 4. And what we did was we were putting our eye down that bond axis, okay? So let me fill in the things that may not be obvious. Okay, so obviously we have these hydrogens. And I'm just gonna write in blue, oops, I'm just gonna write in blue, why did this rotate? Oh, sorry about that. And I'm gonna write in blue CH3 and H3C. Okay, so that's just butane, and you know we know what butane looks like. Okay, so when we're looking down this bond axis, we know that our first carbon, or carbon number 2, is going to be a dot on our paper. And if you can imagine going through this whole thing again, this would be what you were looking at. So if you were doing, you know, going down this bond axis, and you were looking directly, just let me fix this, you would be looking just like that. You see that we have the CH3 group going directly down, and you see that we have the hydrogen coming up on the wedge to the right, and then this is the dash hydrogen going into the page left. And if you can't really see that relationship, let me rotate. So ready, boom, okay? So that is where this came from. So look at that front carbon again. This is the CH3 down here. That's the hydrogen up to on the wedge right here. This is the hydrogen on the dash back here. And you're supposed to look at it from this perspective. Okay, so that's why we got this. Okay, so that's the first step. The next step is to draw a big circle, and that is now my back carbon, or carbon number 3. Okay, so we see that we have a hydrogen on a wedge, a hydrogen on a dash, and the methyl group going directly up. So that should match on my model. So I'm looking, you know, originally it's like this, and I'm supposed to look at it down this bond axis. So does that match? Yeah, I have a hydrogen on a wedge, a hydrogen on the dash, and a CH3 going up. This is the hydrogen on a wedge, this is the hydrogen on a dash, and that's the CH3 going directly up. So that's why I'm going to draw CH3. This one is that guy, and this one is that guy. Okay? So that's how we get these Newman projections. Is everybody clear on that visual? Okay, I think it's important. All right, I'm hoping. So this specific conformer is going to be called the Anti-Conformation. Okay, and we're calling it the Anti-Conformation because the two largest groups, Bailey, what's your question? You didn't kind of follow that. What specifically about it?
Oh, I was answering Julia's question.
Oh,
Sorry.
okay, gotcha. So we're back here to the anti-conformation. So why is it called the anti-conformation? Well, we're looking at the two largest groups. So on this front carbon, what is the largest group? Well, it's clearly the methyl group, right? And then on the back carbon, what's the largest group? It's the methyl group as well. So these two largest groups, the methyl and the other methyl, are as far apart as they are as possible. Okay, so this one is down and this one is up. Notice how this one is down and up, and look how far away they are from each other. So it's the anti-conformation because these two largest groups are anti. They're far away. They're opposite directions, and this is a very good thing. So I'm going to draw a big smiley face. Okay, this is the best thing that we want. Okay, and the reason that is something called sterics, so steric argument, and that's kind of what we're going to talk about here. So for all intents and purposes, you guys can just imagine these groups, all of these things, the hydrogen, the methyl, whatever they are, as just clouds of electrons or clouds of negative charges. And we've kind of already talked about why negative charges aren't a great thing, but when you put negative charges close to each other, these electron clouds, they're repulsive and not stable. So the fact that we're putting these, methyl groups or these electron clouds that are very bulky far away from each other in this anti-conformation, just like this, is a very good stabilizing feature. All right, now we're gonna go a little more complicated. So a feature about sigma bonds is you can rotate around them, and we're not gonna talk about why, and that's an argument for physical chemistry, but they can rotate around them. So what I'm gonna do is I'm gonna take this same, this is the conformer that we had before. Okay, this is butane, methyl down, methyl up, front carbon, back carbon. And what I'm gonna do is, watch what I do. I am going to rotate the back carbon 60 degrees, okay? So 60 degrees. Okay, notice all I did was keep the front ones the same, and I'm rotating the back carbon 60 degrees. Okay, so what results from this? Well, let's just draw the Newman projection from this perspective, okay? So the front carbon has not changed. Everyone can see that. So what we're gonna do here is keep the front carbon the same. Okay, but then on the back carbon, I quite literally rotated this back carbon 60 degrees. okay? So what happened was is that that top group is now aligned with this right hydrogen. And this kind of staggered hydrogen is now aligned with this bottom methyl. So essentially, how does that translate? We would draw the CH3 on the back carbon here, this new hydrogen down here, and then this hydrogen now is over here, okay? So this is now the result of just, if you can even see it from here, all I did was rotate all of these back substituents just 1 over. So this would be a 60-degree angle, okay? So just kind of follow that. I kept the front carbon same, and the CH3 is now eclipsed with that hydrogen. This hydrogen is now eclipsed with that CH3, and this hydrogen is now eclipsed with that hydrogen, okay? So this one is going to be called the Eclipsed Conformation, okay? And this one is not stable, but it's not the worst one, and we'll get to the worst one in a second. So what does this look like in Lewis structure? I mean, or in this structure? So you still have the front carbon the same. We didn't rotate the front carbon, so everything should still look like this, okay? But in terms of the back carbon, we rotated this methyl group, okay, 60 degrees, and now it's, according to our Newman projection, it should be in line with this wedged hydrogen. Remember, it's on the right side. So how do I make that, you know, visible? Essentially, oh, I drew this wrong, sorry. I'm gonna draw this again over here. So essentially, what we're gonna do is draw this, okay? And if you don't believe me, just draw from that perspective. If you're looking down that bond angle, if you're looking down this bond angle, the front carbon has the hydrogen on a wedge, okay? So that's coming out. And I used to do this with pens. So like the blue dash, the dash is my blue pen, and then the wedge is my black pen, okay? So if I'm going to look from the side, like if I'm looking where this arrow is pointing, okay? And it's like a V, and then I were to translate that on 2D paper, it's gonna look like that, this V. Oops, this V, okay? So again, this wedge hydrogen from this perspective translates to my right. This blue dash, whatever, on the blue pen, is now gonna translate to my left, okay? I'm just trying to give you all the different types of visuals that you can use, all right? So this is the Eclipse Conformer, and this isn't so great because look at these interactions. They're literally on top of each other. So there's all this repulsive interaction happening from the electron clouds being stacked on top of each other. Okay, so not so great. So let me do medium, Sterics. And I think we have some questions. Does it matter if we draw it to the left or to the right? What do you mean by left or right? Kalista, what are you talking about there? If you want to get back to me in the chat box, just get back to me. And Caroline, wait, can you show it in comparison to the line angle of butane? Yeah, so this is the line angle of butane. So this is what it translates to. So this is butane, 1, 2, 3, 4. And what you're doing is all we did was rotate this back carbon 60 degrees, okay? Honestly, it's very hard to visualize it from here to here. It's very easy to visualize it from here to here. All I did was kept the front carbon the same, and we just rotated everything in the back 60 degrees to the right. So this comes down, this goes down, this goes up, okay? And that's what that is. So we're gonna keep going 60 degrees. So now move again, that back carbon again 60 degrees. And I'm not gonna necessarily keep drawing the line angle, but I will keep drawing these Newmans. So the front carbon stayed the exact same, notice, and we're not doing anything there. But if this CH3 group was there and I'm moving at 60 degrees, now it should be staggered. And then this hydrogen is now here, and that hydrogen is now here. Okay, does everybody follow that? All I'm doing is literally all here to here to here. Like you're just keep rotating everything like 60 degrees. Okay, so this type of conformer is called the Gauche conformer. Gauche. And this one is not that stable. I mean, it's better than Eclipsed, but it's not so stable. And the reason why it's not so stable is even though they're not on top of each other, these two large bulky groups are pretty close to each other. So the Gauche conformer is a name that we just give to the Newman projection, where the two largest groups on the front and the back carbon are as close as, I guess, in their staggered orientation that they can be. So essentially it's the staggered conformer where the front and back largest groups are kind of close to each other. Okay, so this is the gauche. So not, it's definitely, let me do maybe like, you know, like when people like sweat, like the sweat emoji, like he's sweating and kind of confused, I guess. Like when you change from staggered to eclipse. So yeah, Kalista, I'm looking at your question, and it doesn't matter if you put it to the left or to the right of the substituent. And Sabrina, it's not always that. I sometimes, like, we just give you fake numbers to use because we don't really care about the number. You're not going to memorize anything. But we'll just kind of give you the numbers, and you just have to know what to do with the numbers, not necessarily memorize any of them. Yep, and so staggered to be anti and gauche. Yeah, so I haven't gotten to there yet, but yeah, so staggered is the overall umbrella term that just refers to anything that looks like this. So it could be an anti-conformer, it could be a Gauche conformer. Those are all types of staggered. And we're going to see a whole bunch of different types of eclipsed as well. Those are umbrella terms. And then the Gauche is just a specific name. The anti-conformer is a specific name, yada, yada, yada. Okay, and so forth. So again, now we're just going to keep rotating 60 degrees, keep going, keep going, keep going. So again, keep that front carbon the same. I'm going to draw this over here. So again, CH3 going down. Okay. And now this CH3 group should be directly, okay, behind. You notice that? So the CH3 group should be directly behind now. This is so repulsive and so bad because they are directly on top of each other, the two largest groups. This is called the totally eclipsed conformer. Okay, and this one is the absolute worst. Okay, absolute worst. And the reason that is, you know, you have these groups that are pretty bulky sterically, and they're pretty close to each other. So the repulsive electron clouds, like, is not favorable. And what does this look like in line angle? Well, now maybe you understand. I hope we're gonna have an aha moment in a second. This is still butane, but when you look down that axis, do you see how this is the cis orientation or not? When you're drawing, you know, line angle formula, like let's say, you know, you were doing nomenclature and you had like a non-name, you always do 1, 2, 3, 4, 5, 6, 7, something like that. 9, maybe that's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you do like this kind of hill, like triangle structure, right? But notice how here, that's not the hill that you're supposed to see. This is, you know, you rotated around that bond, so you got something like that, okay? So this is the cis, I guess this is the cis kind of orientation, and this is the trans orientation. And we always draw it like this, we teach it to you like that, because this is the most stable arrangement. Because notice how, if we're looking down maybe this bond angle, this group and this whole chain are a 180 from each other. They're the most stable orientation. But we don't ever draw things like this because, well, I guess in normal sense, we don't draw things like this because this is the less stable conformer. Because if you were to look at the Newman projection, the groups are kind of on top of each other. And if you still don't believe me, I'm gonna go back to the actual camera in a second, so give me one. All right, can you guys hear me? I hope so. And so again, here we have butane. So let me just pin this. So here we have butane again, okay? And this is the trans format, remember, up, down, that's what you always do. But let's say, what if I did the cis format? What if, you know, I rotated around the bond? So now you see that I have the cis orientation. Okay, so what does that Newman projection look like? So let's now look down this bond. Okay, so we're looking down this bond. And you can see these are the two bottom CH3 groups. Look at this big bulky CH3 group down here. And then we have another big CH3 group down here. And from a side profile, look how close they are. Like the hydrogens are already touching. And you know, like this is a very bulky steric argument. But remember, if it was trans like that, look how far away they are. It's all the way up here and this one's down here. So staggered, the staggered, I guess, anti-conformation is the best one, where the biggest group, the methyl group, is up here far away. The biggest methyl group down here is far away. But when you rotate them, they're eclipsed. And this is very sterically, I guess, not favorable. Okay? Everybody kind of get me so far? Yeah? Someone put something in the chat box? I know. Oh, and that's my cat, Wiki. He's sleeping, I think. Cool. All right, let's go back to the other side. Okay. So does everybody kind of understand the logic here? Like that's like the main ideas. Now we kind of just took a whole digressed and did all that. So now we're just gonna be able to do problems. That was the theory. Let's kind of go into problems. So the first thing I kind of want to just touch upon, because it's sometimes asked very minimally, is this notion of this notion of wrong page. This notion of constitutional isomers. Okay, so we're definitely in the chapter 2 material, which is the isomer section, and you guys will be I don't want to say memorize, you guys will be understanding that isomer tree very well. So as of right now, we're going to add to this every day. So every session we do, but we are now talking about isomers, okay? And we have two main branches of isomers. So is it a structural thing? Is it a connectivity issue? So connectivity, okay? Or is it a 3D space issue, okay? And we're not really on, well, we're gonna touch on this in a second, but today we're gonna first do connectivity. And these are gonna be called constitutional isomers, okay? And I know this is kind of an incomplete tree, but it will make total sense and you'll be able to recite it, you know, with logic by the time we're done. So constitutional isomers, so here we are. And we have some questions. Are EOC problems the end of the chapter problems in the workbook? I mean, in the textbook? Never do a textbook problem there. Seriously, the book is way too complicated in my opinion. That's why we wrote the student workbooks. Don't even open the book. Don't even open the book. Yeah. Can you go back to the tree? Yes, I can. All right, so here we are. So copy this down. We're gonna add to it, and it's gonna make sense. I promise. I know it's annoying to memorize a tree, but it will make total sense. So today we're kind of dealing with this first kind of branch, the connectivity issue with constitutional isomers. So we're on page 33 in the student workbook. Yeah, you can read this on your own. Basically, butane. So here we are, butane. The first thing you want to do is draw what butane looks like, okay? And what I typically do is I cut off a fragment, okay? So let me just say I'm going to cut off this CH3 fragment, this one at the top. And I'm going to cut and paste it, so I'm cutting it, and maybe let me paste it on the next carbon over. So if I cut the CH3 group and I put it there, the resulting structure might be something like that. And that is a constitutional isomer of butane. How do I verify that? Well, let's just see. So I have C1, 2, 3, 4, so C4, and H3, 6, 7, 8, 9, 10, so H10. So you always want to verify the molecular formulas with these. So butane, yep, C4H10. Okay, is this C4H10? Yeah, it's C1, 2, 3, 4, so C4, and then H10, 3, 6, 9, and then don't forget that one in the middle, so that's H10. Yep, this is definitely a constitutional isomer of butane. So you can see all that's changing here is the specific connectivity of my chain. You know, we could have, you know, a hexane, let me think, a hexane that looks like this. 1, 2, 3, 4. Actually, we're going to get to that, so I'm going to jump the gun. But and then in this case, there was only 2 of them. But let's kind of think of another example. Maybe let's take this methyl group, and what if I put it, instead of this carbon, let me put it on the end. So the resulting structure would be something like that. And this looks pretty similar to what I had before, but it just looks like it was kind of pancake flipped. And with constitutional isomers, you can never repeat the same structure. And I think I write that up here. When considering potential constitutional isomers, it's a good idea to count the number of atoms, which we did to verify that the molecular formulas match, and then verify your inquiry by making sure that the structure you just drew is not identical to any structure you already had via flipping and rotation. So notice how this is the same as that, just flipped, and we can't draw that one. So you basically just guess and check. You just try a whole bunch of different combos of fragments and moving them around and seeing which ones match. And you're never gonna get anything higher than heptane. So honestly, if you know these 4, you're in good shape, because beyond heptane gets too complicated. There's too many. So pentane, let's try pentane. 1, 2, 3, 4, 5. Okay, so I got more isomers than the answer key. Is that okay? Probably not, Kelsey. I'm sorry. Do you want to, for butane, are you talking about? Is that what you're talking about? Is it butane? No, for the last ones. For heptane. Wait, I'm confused. for the last ones, Kelsey? Are you talking about this butane stuff I'm doing up here? Oh, heptane. Okay. You might have a duplicate one that you don't know about yet in there. You have some sort of flipping and rotating, unless Dr. Peterson might have left one out. So I can check that at the end of the session. So pentane, so here we go. So same exact logic. We are going to cut off maybe the CH3 group and maybe let's move it below. So let's do, so remember this is now 4 carbons and I took off that last CH3, let's call it 5, and I maybe moved it here, okay? So clearly that's a structure. I like that one. I could also take that, same 5 methyl group and maybe let's move it onto this carbon. And if I did that, it would be that. Oh, but this looks just like the same exact thing that I just drew. So, it just looks like the pancake version of that going from here to here. So yeah, I don't want to draw that one. That one's the same thing. Okay, let me try that again. What if I took this methyl group and put it all the way at the end, the other carbon? Well, that would look like that. And that's the same exact one as my original. So no, that one can't work either. So do you see what I'm doing? I'm just taking fragments off at a time and seeing if anything changes. So now, instead of taking off maybe a methyl group, what if I take off an ethyl group? So let's just look at it. Maybe if I take off this 2 carbon chain. And if I take off that 2 carbon chain, what if I put it here? So yeah, that's definitely something I haven't seen before, at least I think. But then when I kind of rotate it a little bit, yeah, it pretty much looks like something I already have. So yeah, the ethyl group doesn't really help me there. Even if I moved it at the end, you can see it would be a duplicate. So right now, it kind of seems like I'm pretty stuck. So the last thing that I could probably, I guess, do is maybe just take off a methyl group from the end and put it in the middle, okay? And then take off another methyl group and put it here, okay? So let me just kind of scribble more so you guys don't get confused about which ones are duplicates, okay? So these are kind of the 3 that I get here, okay? And I want to verify these structures, maybe C1, 2, 3, 4, 5, so that's C5, and then H3, 6, 7, 8, 9, 10, 11, 12, H12. Same thing here, 1, 2, 3, 4, 5, C5, and then H3, 6, 9, 10, 11, 12, H12, that one works. This one is C1, 2, 3, 4, 5, H3, 6, 9, 12, H12. So yeah, so those are 3 constitutional isomers of pentane. And again, you just take fragments off, glue them somewhere else, check the molecular formula, make sure you didn't verify it, make sure you can verify them that they're not the same from something you already drew. And honestly, guys, since you're online, my guess is you guys are going to have like multiple choice, like here are, which of the following, select all the following that are constitutional isomers. And that is so easy, guys. All you have to do is just count the atoms, okay? And if they have the same molecular formula on the test, then those are constitutional isomers. Does that make sense? You're not gonna probably have to do this, but it's still a good skill to know because maybe Orgo 2 will be in person in the spring. So just make sure that you guys still know how to do this, even though on a multiple choice test, I don't think it's gonna be this hard, all right? Life hack. Yes, you're welcome, everybody. Hexane and heptane, I'm going to leave you guys to do on your own because they're a little bit longer, so you'll get more structures. Just practice them. Really, I think heptane is borderline too complicated with 7 carbons. But yeah, so again, as long as you guys know these kind of brief ones, you guys will be pretty golden for constitutional isomers. All right, so let's kind of move back to the different types of isomers. So we are back to this tree. So we now know what constitutional isomers are. They are the ones that differ in connectivity. So let me just draw this, butane example, and maybe just draw another one so that you guys can understand. So it's this versus that, this and that, and these are butane. So you guys can now understand that. And maybe I'll just box it in red so you guys know that the examples are in red. Okay, so now 3D space, and there's 2 types of ways that we can differ in 3D space, and that's where we're gonna have our first kind of branching here. And today we're gonna only talk about one of these branches. So we're gonna talk about conformational isomers. And then the other one we're going to talk about is configurational, and we're going to deal with that next session, okay? So don't worry about this right branch yet. We're kind of only staying to the conformational isomer branch. So what we saw already was connectivity, okay? So that was just picking things up, copying and pasting. Now with 3D space, we're going to talk about actual movement, and that's kind of, you guys obviously did that earlier, even though it may not have been obvious. What we were doing is we're rotating, okay? So what conformational isomers is, it's differing in 3D space via rotating. So I'm gonna write maybe in this line, rotations. And this is gonna be something called configurations. And we're not there yet, but we're on rotations right now. So there are conformational isomers. Every single Newman projection that you draw is a conformational isomer of the other one. So an example of that would be like this. And I think this might, be familiar to you guys. I guess I'm writing sideways, sorry about that. And, oops, that's fine, I guess it's okay. And then here, and here. Okay, so notice that we've seen these before. We kind of proved these earlier today. And if you were to look at this, this would be the trans orientation of butane. Okay, that's the trans orientation. And this one is the cis orientation of butane, remember? So this was just because we rotated, around these bonds. So that would be conformational isomers. So that was kind of the aside that we did earlier. So we know what constitutional isomers are now. And if they differ in 3D space because I rotated, these are conformational isomers. And that's kind of all we're going to do with our tree today. So does everybody kind of follow where we're at with these trees? Okay. Good. I hope. All right. So let's move on to actual problems of Newman's. So we are going to be on page 34. Let's make some room. Okay, so here we are. And for the molecule, I guess let me read this before. So again, I said this all in words, and these are my words. So if you guys follow these sessions, you guys would probably understand like the wording here a lot better too, because it's like me also speaking. Whereas constitutional isomers were molecules that differed based on their connectivity, this type of isomer is due to differences in the 3D arrangement of those substituents. And for Newman projections, we're going to use that as a tool to rationalize the stability of that isomer due to the sterics. And we kind of already saw that, okay? So now maybe this is making a little bit more sense, those eclipsed interactions, that it talks about the stability of isomers. So this arrow is kind of indicating what axis I want to look down. So this is my carbon 1, my carbon 2. So in my current Newman projection, and the way that it's depicted here, my front carbon is this dot, okay? And then going directly down, it looks like, from this side view, and what I always tell people to do on like paper tests when I used to proctor was pick up your exam, okay? Let me actually go back here. This to you. Okay, so I always said to people, pick up your exam like this. So like this is your paper exam. You pick it up and you go like this, okay? And I always saw people doing it on their tests, like in the actual lecture halls. And what that's doing is you see that we're pointing down this bromine. So by putting the paper in between like your eyes, like you're doing what that arrow is telling you to do, okay? So I know you don't have paper like tests this semester, but that was definitely a good thing in terms of practice, I thought. Okay, so again, we're going directly down is this bromine, okay? And again, that was that whole paper thing if you can't see me. And then what's not drawn in here are those two hydrogens going up to the right and that hydrogen going to the left. And that was my first carbon, okay? So on the back carbon, so that's the circle, I have a CH2Cl group going up, okay? So that might be confusing. So we're just looking at carbon 1 and carbon 2 here. And this whole back carbon has this group CH2Cl, okay? You can just draw it like that. CH2Cl, that's the condensed form. And then you also have these hydrogens going down here and here, okay? So for all intents and purposes, you guys can say for now, the wedges, and this is not always true, it's just from this orientation, the wedges, the wedged hydrogens are gonna appear on my right. So this would be, let me call this H1 and H2. This would be H1 and H2, okay? And then the dashes in this drawing here, let's call it H3 and H4, this would be H3 and H4, okay? So just so you guys know, wedges on this side, and in this example, are gonna be on the right side of my Newman. And then the dashes are gonna be on the left side of my Newman. Okay, so that's the current. Is this the most stable? Well, yeah, actually it's the most stable as well, because this is the, what? This is the, guys put it in the chat box. I wanna make sure you guys get it. This is what type of conformer? Give me the specific name. Anti-grade, which is a type of staggered. Great, I see it. Awesome. Okay, so the anti-conformation, that is also a subset of staggered. And this is the most stable because of sterics. Those two bulky groups, the bromine and the CH2Cl groups, are as far apart as they can be. So how do I make that the most unstable one, which is equivalent to the what conformation? What's the least stable one? The most unstable. That one is the totally eclipsed. Yes, I was looking for the word totally. That's important. There's eclipsed and then there's totally eclipsed. The totally eclipsed is the name that we get for the specific one where the two largest groups are directly on top of each other. Totally eclipsed. And this one would be the anti. Oh, I'm sorry, the anti would be here. Okay, so what I'm going to do is I'm just going to keep that front carbon the same. Okay, and I'm just going to rotate the back carbon 180 degrees such that that CH2Cl group is directly eclipsed behind that bromine. So that would be something that looks like this. Okay, I guess kind of following me there. And what does that look like in line angle? Well, that would be something that looks like, and I guess I'll just draw these in. And we're going to practice using the line angle stuff on the next page, but that would be the equivalent line angle. And you'd be looking down here. Okay, so hopefully that makes sense. All right, let's keep doing this. So we're looking down here. So the front carbon is going to have a methyl group going down, and then two hydrogens going up to the left and to the right. Okay, so that's pretty easy. Then on the back carbon, we have this. So when it gets like really branched like this, I don't want to write the condensed form. I mean, I could, but what I really could do is this. You can draw a line going up, okay? And that's this bond right here. And then you have this Y. Okay, so it's the isopropyl group on the back carbon going up. So you can draw, you know, the line angle versions of that as short notation, but also be able to do like CH32. So you could also, I guess, I'll draw this in the next one over here. This is also, since this is already the most stable because it's the anti-conformation, we basically can also draw this as, I'll draw you the alternative, CH32. Be able to recognize that that's isopropyl. Okay, so that would be the anti-conformation. Again, they're the same thing. All I did was condense that line angle to a condensed notation. Okay, and the same thing for the least stable. You're just going to rotate that back carbon so that that large bulky group is 180 degrees on top of that methyl group. Okay. This would be CH3, 2, hydrogen, and hydrogen. All right. So that would be the most unstable one. All right, so you guys are kind of getting it, I hope. Okay, so let's do a little bit more of a complicated example. Let's do F, because F looks complicated. All right, so we're going to draw a dot. Okay, now we're looking from this opposite direction, and I'm going to draw in anything I don't explicitly see, so maybe that would help me. Okay, so it looks like if I'm looking up through here, you know, and I put my head like kind of over, let me draw an eye from the side view, it looks like I have an ethyl group going directly upwards. So I should draw CH2, CH3 going up. And then it looks like as the dash going in, that's going to be on my right down side, and that's a methyl group. Okay, so I'm going to take a pause for a second and make sure everyone digests that. Okay, so if you look at it from now, I mean, I'm going to look at it like, this is so weird. Okay, so this is like where I'm looking right now. I'm going to put my head right here. This is how you're supposed to look at it, going upwards, okay? So you need to do that for basically your questions and your tests. Kind of just move your head around if you need to kind of like look at where you are, okay? So if I'm looking up, I see that that CH2, CH3 group's going up, and that methyl group is right and into the paper, okay? So that's there. And then the back carbon, okay, is that circle. And it looks like I have a methyl group going down on that carbon in the back, it looks like. And that tert-butyl group is kind of up and to the right, it looks like, up and towards the right. So I'm going to draw, you know, actually, I'll just draw this in condensed. So it's going to be CCH3, 3, and we're going to have a hydrogen here, okay? So this is the current conformer that we have, okay? Is this line angle in a cis format? Oh, hold on, we got a couple questions. Caroline, can we do the condensed form? Which will they want? Either or, and you could be given either or. So be able to recognize that this condensed is tert-butyl, and then this condensed up here is isopropyl. So you could be given vice versa. There's no preference. And then, so this is the line angle in a cis format. Yes, this could be actually, no, this is not a cis format, and we're gonna get there in a second. Caroline, I have a question. What's your question, Caroline?
So when you look at it, like for, oh, sorry, it sounds like I'm echoing, but for F, like we obviously have, like they give us one, that's a wedge. I mean, that's a dashed, but like for A, like one of the hydrogens is wedge, one is dashed. So, and when we write that in the Newman structure, then how do we know like which side, like I don't know if that makes sense, like which side we'd write it on, like for the
Yeah,
hydrogen,
so I get what you're saying. I get what you're saying. Essentially, everyone every semester always tries and memorizes, oh, wedges mean right, dashes mean left, and that's not true. It's always based on perspective. So this is what is true. If you're looking from the right side and you have wedges, those are going to be on the right. Does that make sense? Like just from this perspective, maybe you can see that. From this perspective, from the left, anything that's a wedge is on the right, and anything that's on a dash is on the left. That's always true. But the minute you flip perspective, going like looking from, I guess, the right side to the left, then everything flips. So your wedges, which were on the right side here, are now on the left side. So that's always true. You can actually remember that if you want, but you can't just say wedges are always right or dashes are always left. Does that kind of answer your question? It's just based on perspective.
Yeah, I think like, yeah, I think so. Like, so if you look from the right, then the wedge would be on the left for the Newman structure. Like for F, like when we're looking on the right, or for D even.
Yeah, exactly. So if you're, yeah, so let's do C, D, and F. Anything that's on a wedge is going to be on the left side of my Newman. Anything that's on a dash is going to be on the right side of my Newman. Now let's take a look at A, B, and E. Since we're looking from this perspective, anything that's on a wedge is on my right, anything that's on a dash is on my left. So that is something you could, I guess, memorize, like if you really wanted to. But yeah, it's based on perspective. I don't memorize that. Yep. All right. I'm out of breath. Can someone type this in for Nyessa? I hope I said your name right. Correct me if I'm wrong. Someone type what I just said. I have no breath left. All right. All right. So that would be the. Thank you, Abby. So that would be the current conformer that we have right now. Most stable would be the one where we would produce those two largest groups such that they are, the farthest apart. So let's just leave the front carbon the way that it is. So let me leave the CH2, CH3 up top. And everyone's could be slightly different, as long as you're consistent. So this is my front carbon. And I want to rotate the back carbon such that, is the methyl group or is it the tert-butyl group, the more bulky one? And it's the tert-butyl group. So I want to rotate this tert-butyl group, this CCH33 group, such that it is 180 degrees from the ethyl group. So basically, just follow my arrow. I'm going to rotate such that we have this. Okay, so that's the most stable, because now this ethyl group, which is the bulkiest thing on the front carbon, and this tert-butyl group, which is the bulkiest thing on the back carbon, are now 180 degrees apart from each other, and they are trans. So that's very stable. Okay, and the alternative would be to make the least stable one, and that would be to eclipse these two big groups. So let's keep the front carbon the same. Oops, this should be a 2. And we'll do hydrogen and CH3. And then now what we want to do is, I'll draw this in blue. All I can do is rotate the back carbon 60 degrees the other way so that I get CH33, and this would be CH3, and this would be hydrogen. Okay? So I think you guys are kind of getting this logic. It's really easy. You just have to rotate everything. Okay, cool. Yes, and everyone, if you want to read what I was saying, Abby wrote a really nice explanation. I hate memorizing, but if you want something to memorize, you can memorize that. Caroline, is that anti and gauge? I meant that for the first one. The first one is the anti-conformer, and it is not gauche, okay? Oh, I'm sorry. well, here. This one is Gauche. Okay, this one is Gauche. This one is anti, and this one is totally eclipsed. These are the names, if you guys care. Okay? That's that. Yep. And for example, wait, how is the CH2Cl? That is a great question, Juliana. Okay, so let's go back there. It's a great question, honestly. So yeah, it looks like the Cl's going down, right? And people are like, how is this up? And you don't look anything, you strictly look at this. You always want to look at like basically 4 things. The down thing, the main bond access, and then the up thing, okay? I guess that's 3 things. So all I need to know what's going up is the fact that this line is going up. I don't care about anything else beyond that, okay? So the fact that I saw this group up is why I drew CH2 up, and whatever follows, you know? I know it looks like it's going down, but we're looking at this main bond, and that bond was directed upwards. Good question there. All right, so that's Newman's going this way. I think this is pretty easy. So like in terms of going this direction, the opposite direction going from Newman to line angle is a little bit more tricky. Okay, so is there any more questions here? Yes, I guess we do. Also, will we ever rotate the front carbon? Yeah, you can do whatever you want, honestly. It's all up to you. You can either keep the front carbon fixed, rotate the back one, you know, do the opposite, you know, anything that you want, as long as your structure looks like our structure somehow, okay? As long as you're consistent with like what's alternating or what's on top of each other, things like that, that's what we look for. It's multiple choice, I guess. So you guys will be pretty good on this test. All right, let's go to the next guy. So this structure, we actually did this earlier. So this question is a favorite. This is very good. I would know how to do this one. Wink, wink. So butane is what we were talking about earlier. And I already drew out all of these butane structures for you, all the Newmans, all 6 of them, okay? And now what we want to do is here's an energy plot. And dihedral angle, ignore that. Fancy, fancy, fancy. All you need to know is that energy. And the higher you go is higher energy, and the lower you go is lower in energy. Okay, so the higher energy things are always the eclipsed guys. And we knew that because those were the steric arguments. So eclipsed should be kind of up here. And then we could think anti should be kind of down here. And that just kind of makes sense. Lower energy is the one where the electron clouds are far apart from each other. And the higher energy are the ones where they're on top of each other and sterically unfavorable. Okay, so let's kind of just do that briefly. Let's just look at the eclipsed ones first. So let's look at, looks like B, C, and F. So right now I'm just looking at B, C, and F because those are clearly my eclipsed ones. So those should be the top 3. Okay, so we have the top 3 and the bottom, I guess. I drew too many. Top 3 and then the bottom 2. I'm sorry, top 3 and bottom 3. That's what it is. I drew an extra box for some reason. My bad. Okay, so what is the worst one? That's all the way at this peak. And this one has to be the totally eclipsed conformer, where the 2 largest groups are directly on top of each other. So everybody in the chat box, put that letter. What do you think it is? A through F. C, yep, C. Awesome, great. So you guys got it. So C, clearly the worst one. Eclipse is always the highest because look how sterically, bulky that is. That's pretty bad. Then the next ones are going to be either B or F. So these are pretty much equivalent. So that's why they're kind of on the same energy line here, B and F. So it doesn't matter if I put it here or here. So you can put B where F is or F where B is. You could, interchange those. It doesn't matter as long as, they're on that energy plot. Okay. And then that's it for the B, C, and F guys. Now let's talk about the staggered ones, A, D, and E. So A, D, and E. So the lowest one is going to be the anti-conformation, where the 2 largest groups are so far apart from each other. So again, in the chat box, everybody, what do you think it is? E, yep, love that. E is the one down here, because look at these groups. They are totally far and separated from each other. That's pretty good. And then A and F, A and D. So these are pretty much equivalent. Notice how these 2 largest groups are close to each other. This would be the Gauche conformers. So the Gauche ones, again, you could vice versa it. So A could be where D is and D could be where A is. And you can kind of rationalize now going from the, y-axis where it's 0 to the y-axis is where it's some sort of number. You go from anti to Gauche to eclipsed to like totally eclipsed, I guess. And that makes logical sense. So this is a very important question, rationalizing how to equate, I guess, different isomers in terms of their stability. with these Newman projections. That's a very important skill that you guys will be tested on in this fashion. So know how to do this question. All right. And then let's just finish with this last type of question, and we'll be good for the day. I know we're at 12:50, but I can keep giving you guys a few more minutes. How do I do this? So essentially, what you want to do is when you see either staggered or eclipsed, you can do either one of two things. When you see staggered, you always draw trans. When you see eclipsed, you always draw cis. Okay, so staggered, so like this, is always going to be something called trans. Okay, and eclipsed is always going to be something called cis. Okay, so what does that mean? Well, trans, is line angle like this. Cis is something like that. Okay, so every time you see a staggered conformer, it's always going to be some sort of trans line angle formula. Every time you see an eclipsed conformer, you're always going to draw some sort of cis line angle. Okay, so what does that mean? What you want to do is, this is a staggered one, so I know I'm going to draw trans. What I do is I put my pencil or pen, whatever, directly at the top or the bottom thing on the front carbon. So here it's going up, and I trace my pencil, watch, down. You can't see it, but I'm going through the paper now, and then back down. Okay, so down, into the paper, down. So that equates to down, into the paper, down. You guys follow that? Down, into the paper, down. Okay, down, I'm gonna do it again, into the paper, down. Down, into the paper, down. Okay, cool. Now, you just view it like you normally would. So on this front carbon, it looks like I have a hydroxyl on my left. So if I'm viewing it from this perspective, that hydroxyl has to be on the left. Okay, so let me just draw it like this. So the red pen is the hydroxyl and the black pen is the hydrogen. So if I'm going to flip it such that it fits this line angle structure, it would be something like, yeah, these pens are too high. So see how the red is like going into the paper? So that would be the hydroxyl group. And this black is coming out, and that's the hydrogen. So that would be the front carbon, okay? So again, you're just translating it to the left over here. Doop. All right, and then the back carbon, we see that it looks like up and to the right, which would be up and to the right over here on a wedge, is this, what is CH2? Somebody put in the chat box, what is that condensed form of? It's one of your common groups that you know. Yeah, isopropyl, great. There's really, it's just two of them. It's like really CH2 or CH3. Those are like, that's tributyl. So anyway, so I'm just gonna draw it like that. That's isopropyl, and it doesn't matter, you could draw it as those condensed letters as well. And then the other one on a hydrogen. And you don't have to draw these hydrogens either. I'm just showing you right now because we're kind of in the basic version. And that's that one. So that's so the first thing you want to do is see, is it staggered or eclipsed? If it's staggered, you draw a trans framework and then you just fill it in. Now we're going to try the eclipsed example. So again, these images are just slightly staggered just so you can see everything, but they are eclipsed. So what I want to do is, I know it's eclipsed, so I'm going to draw a cis. So let's trace this. It's going to be down through the paper and then back up. Okay, so down through the paper, back up. Do you see that? So on my front carbon, it looks like I have a hydroxyl group coming to my right. So if I'm looking at it from this perspective, I would want it on a wedge. And then this methyl group should be on a dash. Okay, so it's the front carbon. And on the back carbon, on that top group, it wasn't just CH3, it was CH3. So that's actually tert-butyl. And then it looks like down to the right, I had a CH3 group. So notice how if the hydroxyl group was on a wedge, that CH3 group should also be on a wedge. And if that CH3 group was on a dash over here, that chlorine group should also match the same kind of orientation, like that. Okay, so I think I had a question. No, that's actually okay, Caroline. You could draw it from the right as well, and it would just be the flipped, and it would also be equivalent, 100%. Exactly. So again, this is all open to interpretation, but there will be consistency, yeah. And again, this is always how I do it. Staggered is always trans. Eclipse is always cis. So that's the first thing you want to do. Draw the trans or draw the cis. I always like look at from the eye going this way, but you could also do it from the eye going the other way and draw the alternative. Okay, so this is definitely a harder scale going this direction, but I don't think it's too impossible. Let me do one more with you guys and we will be done for the day. Okay, so this one is a staggered conformer. So staggered tells me trans. So that means I'm going to trace what the orientation was. Actually, I want to do a different one. Let's do F. So again, still staggered. Okay, so I know it's going to be trans. Let's trace it. So it's up through the paper, up through the paper, up. See that? So now I'm going to look down there. This is a hydrogen, and this would be the back hydroxyl group. And then what we want to see here is that on the front carbon towards my right is going to be this 1, 2, oh God, this is going to be a isobutyl group, it looks like. So it's going to be a wedge, and it's going to be, you can just draw it if you don't know that that's isobutyl, but so I'm just going to do that for now. You haven't seen that one. And then it looks like on the wedge, it's just going to be a methyl group. Okay. And then on the back carbon, it looks like we had a, I guess, tert-butyl group going here. And then on the back, it was a hydrogen going there. Okay. So again, I know I'm doing this quick, but you guys will definitely get better with practice. Definitely take the time to go through C, D, and E. And I will see you guys on Wednesday for the next type of isomer for our tree. All right. Hope that helps, guys.
I had a quick question.
Yep.
Well, I came kind of late, so I'm not sure if you covered this before.